Hello my dears. So now we are going to discuss about op-amp as an inverting amplifier and the concept of virtual ground. So how we can use this op-amp as an amplifier? That's our question. So in the previous class we discussed simply a bare op-amp. Bare op-amp in the sense there is no feedback and all. See, I already discussed the characteristics of the transfer characteristics of my op-amp. That is like this. Is it clear, my dear? So this will be plus V sag and this will be minus V sag. So normally if we need an amplifier circuit from a transistor or from op-amp, anything, so what we are normally doing, we are operating our device in this linear region. Then only the gain can be controllable. If you are operating this device in saturation region means, saturation region means what happened? We control our gain, because whatever may be the difference in input, the output will be a constant V sag. So this region is not suitable for the transistor as a what? Amplifier, or op-amp as an amplifier. So for amplifying, this region we are preferring, or this region we are preferring. That means there will be a linear region we need for the amplifying action. So why we are referring it as a linear means we can produce or we can change the gain of an amplifier. We can vary the gain of an amplifier simply by adjusting the components which are connected, or simply resistance which are connected across the BJT or across the op-amp. So here also normal it will be a bare op-amp. It contain plus V and minus V. Okay, normal it contain, but we can't control the output voltage by controlling the components. But now in the case of a feedback system, so what is mean by feedback? Mean taking the output which is connected to the inverting terminal. It is called the inverting feedback. It is called the inverting feedback or negative feedback, simply negative feedback. And another feedback, you can take a terminal from the output and you can connect it to the positive terminal, which is called the positive feedback. Normally positive feedback increases the gain because it adds the overall gain again, and it make the system to instability more. But normally we are using for amplification, we are using the non-inverting, we are using the negative feedback. Positive feedback we are using in the case of oscillators, that we will discuss later. So in the case of amplifier we are using the negative feedback. It is very important for amplifiers. Negative feedback, and for oscillators positive feedback. For oscillator positive. This is very important, my dear. Please note it. Okay, and so now we are connecting a feedback resistor RF, and we are giving, because it is a inverting amplifier. Inverting means we are giving we are giving the feedback to the negative terminal, as well as we are giving input to the negative terminal, making the non-inverting terminal 0 volt. So this is nothing but 0 volt, or simply grounded. The symbol is nothing but grounded. Okay. So before we are moving into the inverting amplifier action, we need to focus on virtual ground property. This is a very important property in op-amp, my dear. If you know the virtual ground property, or if you apply the virtual ground property, any problems regarding the op-amp can be solved in any manner. You can solve any problem. So let us discuss first what is meant by virtual ground. What is meant by virtual ground? Virtual ground, I will explain. See, my dear, suppose my op-amp, this op-amp having a gain, let A is equal to 10 raised to 6. You imagine, okay, A is equal to 10 raised to 6. And its output will be, you can't produce that much output. Suppose the output produced will be 10 volt. You imagine, 10 volt will be the output. Then what will be, you can relate like A is equal to A into VD na, V0 equal to A into VD na. So it will be 10 is equal to A, 10 raised to 6 into VD. So what is VD now? 10 divided by 10 raised to 6. Am I right? Which is nothing but, my dear, 10 raised to 1 minus 6. It's like 10 raised to minus 5. So multiply with 10 and divide with 10 means it will be what? 1 10 raised to minus 6 and 10 micro volt. Am I right, my dear? If I multiply and divide with the 10 and 10, it will become, this 10 will go upside, so it will 10 raised to minus 1, so 10 raised to minus 6 into 10 microvolt. This 10 microvolt is a very small quantity. Imagine 10 microvolt, the difference in voltage is 10 microvolt, means what it implies, my dear, which implies, I will write it here, which implies V1 minus V2 is equal to 10 microvolt. V1 minus V2 is equal to 10 microvolt means it is a very negligible quantity. 10 microvolt means very small voltage, very small voltage. So that we can neglect this difference, like you can take like V1 minus V2 nearly equal to 0. 10 microvolt means very small voltage, so you can assume like V1 minus V2 equal to 0, or you can assume like V1 equal to V2 simply. Here you can represent 0. So V1 equal to V2. This is called virtual ground. That means V1 equal to V2 means nothing but, my dear, this voltage, suppose this is V1 and this is V2, means these two voltages are same. That means whatever may be, where is my pen? Okay, whatever may be the voltage here, the same voltage will exist here also. Or whatever may be the voltage here, the same voltage will exist here also. That is its indirect meaning. That means it is virtually like to be a short circuited condition. Not inside the op-amp it is short circuited, my dear, but virtually it is like a short circuited condition. Only in the short circuited condition, the voltage across this terminal this point will be same as this point now. Only in short circuited condition, this point voltage and this point voltage will be same. But here it is virtually shorted, means we can assume V1 equal to V2. That means whatever you voltage here, you can take the same voltage here. That will make our problem in op-amp when you are facing the problem in op-amp more easier. That will make. Okay, I will do a problem in continuation with the class, so that you can clearly concept, how easily we can solve a problem. You will learn. Okay, so now come back to let me check the time, my dear. Yeah, time is there. And see, suppose our aim is what? Inverting amplifier. Okay, so V1 equal to V2 is called the virtual ground. Now we got the idea of virtual ground now. So whatever may be the voltage here, the same voltage will exist here also. Okay, so now we will come back to our inverting amplifier. Op-amp has an inverting amplifier. Op-amp has an inverting amplifier. Okay, listen, my dear. So suppose I am taking I1 be the current which is, or I be the current which is flow here, and the same, because this and this, in between this there will be infinity impedance. Ideally it is infinity, practically it is very high, so that there will not be any current through this. There will not be any current through this now. And if this is I, means the same current I will be flow here also. Am I correct? Is my assumption is correct? Yes, because it is high input impedance is offering, so there will not be any current flow through this. So if I am sending a current I here, the same current will be flowing here also. There will not be any difference in current here. There will not be any current through this region. Correct now? This will be high impedance region now, so there will not be any current I. So suppose the voltage across this is this point Vx. V1 or simply Vx. Okay, I am taking it as Vx. So I am applying the KCL here, KCL current, Kirchhoff current law here. So at the junction one current is entering, at the same junction one current is leaving. So I can write like, or applying KVL, how can I write like V input minus Vx divided by I R1 equal to Vx minus V0, Vx minus V0 divided by Rf. Am I right, my dear? Am I right? This can be easily. The current here will be starting into minus ending end voltage divided by the resistance. Here also the current will be current starting end from Vx now, current ending will be V, so Vx minus V0 divided by Rf, simple equation. And but Vx equal to what, my dear? 0 volt. Now Vx equal to 0 volt by virtual ground. By virtual ground property. By what? Virtual ground property. So what will happen? This is 0 means this is also 0 now. So Vx will be 0. So in simply V input divided by R1 is equal to minus V0 divided by Rf. Or in other words, V0 divided by V input equal to minus Rf divided by R1. Am I right, my dear? V0 divided by V input. Right now, V0 divided by V input is equal to V0 by V minus Rf by Ri. This is called the what? Inverting amplifier equation. Inverting amplifier equation. V0 by V input equal to minus Rf by R1. So if you observe this, the output having phase shift of 180 degree, because minus Rf by Ri na. If you are giving any input, what is the indication, my dear? If you simply adjusting Rf and Ri, you can control the output value. First thing, the output will be out of phase with the input, that is 180 degree out of phase with the input. Second thing, these two things you can observe from here. So inverting amplifier is nothing but we are giving some input, the output will be inverted amplified version, that's all. Simple. And you got the concept of virtual ground also. Okay, so now we are going to do a very beautiful problem regarding the virtual ground, so that the idea of virtual ground now, how it will be applied to a complicated circuit, you will understand that, and it will be very useful for competitive examination. Okay, let's do a problem. Let's do a problem. Okay, write a question, my dear. Write a question. Question is find V0. That's the question. Okay, this is an op-amp circuit and you have to solve for that. Okay, resistor values are given 1k, 1k, 1k. This is 2k. How can we solve? So by using the property of virtual ground, I am representing a voltage here like Vx, and same voltage will be like Vx also. First my assumption. Okay, and I am also assuming a current of I is flowing here and another current of I, or simply I dash, is flowing here. A current I is flowing here and a current I dash is flowing. The same current I will be flowing here also, because it is infinite impedance. So the same current will be flowing here also. And here also infinite impedance, so the same current flowing here also, I dash. These are my assumptions. Okay, and I am applying the KVL in this loop. So what I get? Second, this is 1 volt. So for I dash, for I dash I apply like 1 minus Vx divided by, this Vx is not 0 my dear, because its resistance is somewhere, it is not directly grounded, its resistance is there, so you can't take it like Vx equal to 0. But 1 minus Vx divided by 1k equal to the same current ideal flowing here also, from here to here will be same as current from here to here. Current from here to here is nothing but my dear Vx minus 0 divided by 1k. Am I right? The current from here to here in this loop means this end voltage minus this end voltage divided by resistance. 1 minus Vx by 1k, 1 minus Vx by 1k. And here Vx minus 0, this is 0 volt now. So Vx minus 0 divided by 1k will be this current. The same will be equal. This one again 1k over. So I can write like 1 is equal to 2 Vx. Am I right, my dear? Am I right? Am I right? Because 1k means 1. 1 minus Vx equal to Vx. So 1 minus Vx equal to Vx, or 1 equal to 2 Vx, or simply Vx equal to 1 by 2 volt. So Vx you got like 1 by 2 volt. Okay. So now you got Vx value. So for I can same equation I can apply. Current from here to here means 1 minus Vx. 1 minus Vx divided by 1k will be equal to current from here to here means what it is. Again Vx minus V0 whole divided by 2k. Am I right, my dear? But Vx, you know the value Vx equal 1 by 2. Okay now. So 1 minus 1 by 2 divided by 1k equal to 1 by 2 minus V0 whole divided by 2k. Am I right, my dear? So I can write like this k and k got cancelled. Both sides 1000, so it can be cancelled. So 2 minus 2 into 1 by 2, it is 1 equal to 1 by 2 minus V0. Simply 2 minus 1 is 1. 1 minus 1 by 2 equal to V0, or simply V0 equal to 1 by 2 volt. See how beautifully we obtained the answer. How beautifully we derived the answer by concept of virtual ground. Did you get the idea now how this virtual ground property is useful for solving such question? So any question regarding the op-amp, if you see, you can directly apply the virtual ground property, my dear. If no voltage is given, you itself can assume a voltage like Vx and Vx, you can solve for that. Finally, you will get the answer. So that's all for today's session. So let's meet again tomorrow with a new session. Until then, bye. Take care.